Suppose you have a vector field which is given to you as, so let f of x, y, and z is defined as the first component, y squared, the second component, 2xy plus e to power 3z, and then you have 3y e to power 3z. Assume that this vector field is conservative vector field. I'm asking you to find function f, potential function f. So this is potential function f such that the gradient of potential function is equal to your vector field. For those of you who are going to take differential equation later, you're going to apply this technique in finding the solution of a differential equation as well. So we're looking for this function. Note that we are looking for f of x, y, and z such that it satisfies this condition, such that the gradient of f, which is equal to partial derivative of f with respect to x, partial derivative of f with respect to y, partial derivative of f with respect to z, is equal to your vector field, which is given to you here, y squared and 2xy plus e to power 3z and 3y e to 3z. So what's the meaning of that? It means that my first components must be equal to each other. My second components must be equal. And finally, my third components are the same. So we're going to use these equalities and eventually find this mysterious potential function. So since partial derivative of f with respect to x is equal to y squared, what's the meaning of that? It means that if I take the integral with respect to x, the integral of f of x with respect to x is equal to the integral of y squared. So it means that on the left-hand side, I end up with f of x, y, and z equals to y squared x plus not just a random constancy, plus a function, plus function g of y and z. This is the tricky part. Since you have a function in x, y, and z, when you're taking the partial derivative with respect to x, the part that has only y and z disappears. So when you are taking the integral, you must add a constant in y and z. In y and z. So this is the mysterious function. It has first term y squared times x plus some more terms that we need to figure out. What I'm going to do, I'm going to use blue components. You can say that, hey, since partial derivative of f with respect to y is equal to 2xy plus e to power 3z, I already know my function has some elements, y squared x plus g of yz. So if I take the derivative of f with respect to y, it must be equal to 2xy plus e to power 3z. So let's do that. We're combining these two together. Partial derivative of f with respect to y is going to be 2yx plus g y of y and z equals to 2xy plus e to power 3z. just pure algebra. From algebra, we can get rid of the common opposite terms. 2xy and 2xy, they get cancelled out. Partial derivative of g with respect to y is equal to e to power 3z. So g of y and z is equal to the integral of e to 3z dy. So g of y and z is equal to, here you have y e to power 3z plus a function in z. Let's take a look at this. I'm building function f from scratch. Y squared x plus g of y and z. G of y and z can be written as y e to power 3z plus h of z. It has a constant. Now I need to figure out what is h of z. To find h of z, I'm going to use the green components. Since partial derivative of f with respect to z is equal to 3y e to power 3z, and I know my function f of x and y and z, step by step I'm building this function, is y squared times x plus y e to power 3z plus hz. I'm going to now put this one here. I can combine these two together. Partial derivative of this function with respect to z must be 3y e to power 3z. So let us do that. This guy doesn't have any z in it, so it's going to be 0 plus. This guy has e to power 3z. So it is 3y e to power 3z plus the derivative of h with respect to z is h prime of z. It must be equal to 3y e to power 3z. So now just pure algebra for you. You can cancel out the term on the left, on the right. So h prime of z is equal to 0. So h of z was basically a constant like c. So now just return this back to the function and simplify if you can. F of x, y, z is equal to y squared x plus y e to 3z plus c. This is my potential function.